Okay, so welcome everybody to today's IAMP One World Mathematical Physics seminar. It's a great pleasure to introduce Nina Holden from ETH Zurich, and Nina will tell us about conformal welding in Liouville quantum gravity, recent results and applications. And let me say that, as usual, the seminar will be recorded and made available on YouTube. And I leave the floor to you, Nina.
Okay, thank you very much for the introduction, and also thanks for inviting me to give a talk in the seminar. So I'll be talking about joint works with Maurice Ang and Xin Sun, and also a joint work with Mattis Lehmkuehler. I will be presenting a very powerful technique in random conformal geometry, which is known as conformal welding. In particular, I will present some recent conformal welding results and also some of their applications. I will start the talk by introducing three important objects that will be encountered later. These are the Gaussian free field, Liouville quantum gravity, and the Schramm-Loewner revolution. I also want to explain briefly what conformal welding is. Then in the second part of the talk, I want to present our recent conformal welding results, and I also want to give three recent applications. I actually think there is some noise in the background, so I think maybe there is a microphone which is still on somewhere. Okay, yeah, now it's good. Okay, thanks. Okay, so the first application is to the integrability of SLE. The second application is to random planar maps. And the third application is to the partition function of LQG surfaces with marked points. So first I want to introduce these three important objects appearing in random conformal geometry. So all of these three objects, they are random, and they can in some sense be viewed as planar or two-dimensional. The Gaussian free field is a particular random generalized function. Liouville quantum gravity is a particular model for a random 2D Riemannian manifold. Whereas the Schramm-Loewner revolution is a particular random fractal non-crossing curve in the plane. So all of these, these three objects, they have several properties in common. For example, all three objects they satisfy properties known as conformal invariance and the domain Markov property. The precise definition of these properties will not play an important role for this talk. A second property that all three objects have in common is that they describe the scaling limit of many discrete models. We talk about universality because there is a large class of discrete models which converge to each of these three objects in the scaling limit. So since these three objects have so many properties in common, it's maybe not so surprising that there are a number of interesting relationships and interplays between these objects. And we will be seeing some examples of that later in the talk. So I start by introducing the Gaussian free field. The Gaussian free field, so the free boundary Gaussian free field in the unit disk, it can be defined to be the Gaussian random field, which has mean 0 and which has covariance given by the Neumann-Green's function, where the Neumann-Green's function is defined by this formula. From this definition, one can see that the Gaussian free field is not well defined as a function because this Green's function is equal to infinity on the diagonal. So heuristically speaking, if z is some point in the unit disk, then h of z will be a normal random variable with mean 0 and infinite variance. But it is possible to show that this Gaussian free field is well defined as a random generalized function or a random distribution. So this means that if f is some smooth test function, then the integral of h against f is well defined. So this integral, it will be some random real number, which is normally distributed, which has mean 0 and which has a variance, which depends on the choice of test function. Okay. So to define Liouville quantum gravity, then we let gamma be some parameter between 0 and 2, and we let h be the Gaussian free field in the unit square. A Liouville quantum gravity surface, it is, heuristically speaking, a surface for which the metric is given by the standard Euclidean metric multiplied by e to the power gamma h. So this means that it is the surface with area measure, which has a density e to the power gamma h relative to Lebesgue area measure. It has a measure along its boundary which has a density e to the power gamma h over 2 relative to the Euclidean length measure along the boundary. And it also has a metric or a distance function, which allows to measure the distance between any pairs of points. This is defined such that distances are locally rescaled by e to the power gamma h divided by d sub gamma relative to standard Euclidean distances. Here, d sub gamma is what we call the dimension of the surface. The precise numerical value is actually not known, but is known to be some number depending on gamma, which is strictly greater than 2. So this definition of a Liouville quantum gravity surface does not make literal sense because h is a distribution and not a function. So it's not obvious what e to the power some constant times h means. But it's possible to define both the measures mu and nu, and also the metric or distance function d in a rigorous way by regularizing the field. So for example, in the case of the area measure mu, then we can let h sub epsilon be some smooth approximation to h. Since h sub epsilon is a smooth function, then we can use it to define an area measure, as you can see here. And then it's possible to show that this area measure is converging upon some renormalization as this regularization parameter epsilon is sent to 0. And one can make a rigorous sense of nu and d via a similar procedure. This figure is showing an illustration of the LQG area measure. So heuristically speaking, the different colors is indicating the density of our random Liouville area measure relative to Lebesgue area measure. So the red regions, they correspond to high density regions where the Gaussian field is particularly large, whereas the blue regions, they correspond to low density regions where the Gaussian field is particularly small. So the two measures mu and nu and the metric d, they describe the geometry of what we call a gamma LQG surface. When we work with gamma LQG surfaces in this talk, then we want to view them as abstract surfaces that can be embedded into the complex plane in various different ways. In the figure, we are looking at one LQG surface which has been embedded into the plane in two different ways. It has been embedded in one way into the unit disk, and in one way into this domain U. So we view these two surfaces as the same LQG surface because the measures and the metric that we have in the right part of the figure is just the push forward of the measures and the metric in the left part of the figure under this conformal map phi. So there are many different variants of LQG surfaces that one can consider. So if we go back to this slide, then I said that we let H be the Gaussian free field, but one can also choose H in a slightly different way. So here we have the Gaussian free field on the unit square. One can also, for example, consider the Gaussian free field on some domain with some other topology. One can let H be a field which is absolutely continuous with respect to a GFF. One can let H be a Gaussian free field plus some continuous function, and so on. And for all of these different variants of the Gaussian free field, then all of these, then the constructions I have described on this slide, they still work. And in this talk, we will be particularly interested in LQG surfaces that describe the scaling limit of discrete surfaces known as random planar maps. So I will not be giving any precise definitions about planar maps in this talk, but roughly speaking, a planar map is just a planar graph that has been embedded into either some subset of the complex plane or the sphere. So for example, in the top left part of the figure, here you can see a random planar map with the topology of the sphere. So it has been drawn on the sphere. And it can be, and we assume that it has been chosen uniformly at random from the collection of planar maps with this topology and with a given size. It's possible to show that when the number of vertices of this planar map is going to infinity, then this random planar map is converting to the LQG surface known as the square root of LQG, square root of 8/3 LQG sphere. So this surface can be defined by considering some variant of the Gaussian free field on the sphere. So I will not be describing precisely the notion of convergence that is considered in this result, and I just refer to the works at the bottom of the slide for some more precise statements. So we get, so in this result, we get LQG with what we call the square root of 8/3 LQG, which just means that the parameter gamma of the LQG surface is equal to the square root of 8/3.
Excuse me, is it difficult to convince oneself why this parameter is the square root of 8/3? Or
yeah, so I guess it depends a bit what sort of knowledge one is willing to take as an input. So if you are only considering this definition, then it's somehow not so clear from this definition that this parameter would play any special role. Then if one is willing to take some input which is coming from the physics literature, then in the physics literature there are a number of parameters. So one can consider this parameter gamma. One can also consider a central charge C, and these are related by an explicit formula. And it is possible to argue that this case of the uniformly sampled planar map, it would correspond to what is called the matter central charge equal to 0, which corresponds to a Liouville central charge of 25, and if one uses all the standard relationships between these different parameters, then one does get this value of gamma.
So central charge equal to 0 is the
yeah. So if so there are actually two central charges, but if one takes the matter central charge, then it will be the matter central charge equal to 0, and then it's the Liouville central charge 25.
Thank you.
So that just corresponds to doing a certain reweighting. So if one can imagine that when one sample this planar map, then one takes the Laplacian determinant of the planar map to the power matter central charge, and since this is just uniformly sampled, then one doesn't do any taking matter central charge equal to 0 corresponds to not doing any reweighting of the law at all. So one just gets something which is uniform. So that's why how one justifies the relationship to the matter central charge.
Thank you.
Yeah. Okay. Okay. So next in this figure we have a planar map with disk topology. So again, it has been sampled uniformly at random from some collection of planar maps with disk topology of a given size. And this can be argued to converge to the LQG surface known as the square root of 8/3 LQG disk. In the setting of this figure, then we're again consider planar map with disk topology, but now the planar map has also been decorated by a self-avoiding path connecting two boundary points. In this case, one also gets an LQG disk in a scaling limit with the same value of gamma, but now the field describing this disk will have a logarithmic singularity at the terminal and initial point of this self-avoiding path. So in the first two examples, then we got LQG with gamma equal to the square root of 8/3 because the planar map was sampled uniformly at random from some collection of planar maps. But in the last example, we're getting gamma LQG for some general value of gamma. Here we're considering a planar map such that the probability that our random planar map is equal to some given planar map is proportional to the loop of n model partition function on this planar map. And then the value of gamma that we get, it will depend in some explicit way on the parameter n of this loop of n model. So next I want to introduce the SLE. So the Schramm-Loewner revolution, it is a conformal invariant fractal curve introduced by Schramm in 1999. Schramm was introducing the SLE as a candidate for the scaling limit of statistical physics models. For example, it is believed to describe the scaling limit of the curve of the lattice path known as the self-avoiding walk. And it has also been proven to describe the scaling limit of interfaces in the ESIG model and in a number of other statistical physics models. So when Schramm introduced SLE, he realized that several of the discrete models he was interested in, they were conjectured to have scaling limits having two properties in common. And these two properties are conformal invariance and the domain Markov property. And they prove that there is a unique one-parameter family of curves, which is satisfying these two properties, and they call these curves SLE curves. SLE curves, they are associated with a positive parameter kappa. When kappa is going to 0, then the SLE curve is converging in law to a deterministic path. But when we increase the value of kappa, then the curve is getting more and more windy or fractal. So here you can see illustrations of SLE for kappa equal, or sketches of SLE for kappa equals 2 and kappa equals 4. On the previous slide, we were considering what is called the chordal SLE. So chordal SLE, it is a random curve defined in some simply connected domain, and which is starting and ending at the boundary of the domain. But there are also a number of other interesting variants of SLE that one can consider. In the top part of the figure, then we're considering what we call an SLE with force points. And in some sense, one can argue that the SLE with force points is the most natural way of generalizing the regular chordal SLE. In the setting of the figure, we have SLE with 2 force points. So one has, one of the force points is, these force points are infinitesimally to the left and right of the starting point of the curve. Each of the force points is associated with a parameter rho, and depending on the sign of rho, the force point will have either an attractive or repulsive force on the curve. For example, in the setting of the left figure, then we have rho minus equals 0, which means that this left force point, it will not have any impact on the properties of the curve. On the other hand, for this right force point, then we have a negative rho value, which means that the curve will be pushed towards the right boundary arc of the domain. In this figure, we have a rho plus less than kappa over 2 minus 2, and then this attractive force is so strong that the SLE curve will hit the right domain boundary. So this SLE kappa rho, it is arising in a large number of settings, and it was discovered only 3 years after SLE was first introduced. Okay, so here we have the variant of SLE known as the SLE loop. So this is a loop which has the same local properties as a chordal SLE kappa. So this SLE kappa loop, it is a much less studied object than as compared to the chordal SLE, and it was only constructed for all values of kappa between 0 and 8 about 5 years ago. So this SLE kappa loop, it is believed to be uniquely characterized by some axioms of a similar spirit as those you can see in the third bullet point here. But getting uniqueness is actually still an open problem. So finally, we have the conformal loop ensemble, or CLE. So this is a countable collection of SLE type curves. And this variant of SLE, it has been studied in numerous works, and it was introduced by Scott Sheffield around 15 years ago. So finally, as part of the background, I want to briefly say what conformal welding is. To do that, we let D1 and D2 be 2 copies of the unit disk, and we'll let phi be a homeomorphism between from the boundary of D1 to the boundary of D2. Conformal welding, it is an assignment of a conformal structure to the sphere S2 obtained by identifying the boundaries of these 2 copies of the unit disk according to phi. So it's clear that if we identify the boundaries of these 2 copies of the unit disk according to phi, then topologically speaking, we get a sphere. It's also clear that if we consider the sphere away from this curve eta describing the interface of the 2 disks, then the sphere will have a unique conformal structure. But what is not clear is that one also has such a unique conformal structure across this curve eta. And one can ask both about existence and uniqueness about this conformal structure. So this conformal welding problem, it is a classical and hard problem in analysis. And in general, both existence and uniqueness may fail. But if one has sufficient regularity of either phi or of the curve eta, then one can guarantee the existence of a unique solution. In this talk, we will be considering conformal welding in the setting of LQG surfaces. So I will start by giving some discrete motivation in the setting of planar maps. So in this figure, you can see that we have a bijection between the objects in the left and right part of the figure. So here in the left part of the figure, we have a planar map with a disk topology, and we have a self-avoiding path, which is connecting two vertices on the boundary. So self-avoiding path is just a path which can visit each vertex at most once. So in the right part of the figure, we have a pair of planar maps, and we require in particular that the length of this blue curve is equal to the length of this blue curve. And the projection simply works by taking these two planar maps and then gluing them together along these blue boundary arcs. This projection is illustrating one key strength of conformal welding. If you look at the object in this figure, then the object on the left side of the equality sign is a rather complicated object because of the presence of this self-avoiding path. The objects in the right part of the figure, on the other hand, they are much simpler objects. But due to this projection, if we want to study the object in the left part of the figure, we can instead equivalently study the objects in the right part of the figure. And this is illustrating one key strength of the conformal welding, because often it allows us to divide complicated surfaces into simpler pieces and study the complicated surfaces by using this division. So in the work with Ang and Son, we prove the continuum counterpart of the bijection on the previous slide. So we take two LQG disks shown here in green and blue. And we show that the conformal welding of these two disks is well defined. So when we do this conformal welding, then we're doing it according to boundary length. So if we have some small boundary segment of length epsilon on this side, then we are identifying it with some small boundary segment of length epsilon on this side. So we show that this conformal welding is well defined, and that the resulting object is still given by an LQG disk, such that the interface between the original disks is given by an SLE kappa row curve, such that the SLE kappa row curve is entirely independent of the background LQG disk. As you can see that all the disks that are involved in this result, they have marked points on their boundaries. So each disk has two marked points on its boundary. And at these marked points, the field describing the disk has a logarithmic singularity. And the number you see next to the point is indicating the magnitude or strength of this logarithmic singularity. For example, at this point, we have a logarithmic singularity of strength beta minus. So the field looks locally like GFF plus beta minus times a logarithm. So the row values of the SLE kappa row arising in this result is depending in some explicit way on the parameters gamma and the parameters beta plus minus. The special case when gamma is equal to beta plus minus equal to the square root of 8/3, it's describing the scaling limit of the projection that you can see on the previous slide. So this is a rigorous result, which follows by combining our work with the work of Gwynn and Miller. I want to emphasize that although the result that I present on this slide, it's very much inspired by the discrete, then the proof is done purely in the continuum by completely different techniques. So this result was proved with Ang and Son, but the proof is relying heavily on earlier and closely related results due to Sheffield and Duplanty and Miller and Sheffield.
Excuse me. So what is the input of this theorem? What are the assumptions? So the beta minus and beta plus are given.
Yeah, they are given real numbers. Yeah.
Yeah, and gamma.
So gamma is an arbitrary number between 0 and 2.
Yes. So the earlier results. I mean. So the special case gamma equal to beta plus minus was proven before. That's
No, it was actually not quite proven before. So what Gwynn and Miller proved, they proved that. Okay, so what they proved is that if they look at the scaling limit of this object, they prove that the scaling limit of this object is given by the conformal welding of these two disks. And then the new input in our work is that if you glue together these two disks, then you get this object.
For any parameters, beta minus, beta plus, and gamma. I mean.
Yeah. So our result holds for all gamma and for all gamma and all beta plus minus. We actually do have some restrictions on the betas as well, but it holds for a large range of beta values. And there was no special cases which were known before. So Gwynn and Miller's result is only about the scaling limit of this object. And then by combining the two results, then we get that this bijection is precisely the discrete analog of this bijection. So the objects you see in this figure, they converge jointly to the objects in this figure.
So beta minus is responsible for the singularity of the Green's function close to the North Pole. Is it? I mean.
Yeah. So the way the field is defined, so you can think of the field in this green disk. It is essentially given by a Gaussian free field, and then plus the logarithmic singularity near this point, and plus the logarithmic singularity near this point.
The logarithmic singularity with the coefficient beta minus.
Exactly. Yeah.
And you weld it to another disk where the coefficients are beta plus.
Exactly. Yeah.
And gamma comes through the SLE. Yeah. So
the origin of the gamma is because we have a field. We have this Gaussian free field type field in this disk, and we are getting a boundary measure on the boundary. And this boundary measure has the density e to the power gamma times h/2 relative to Euclidean length measure. So the gamma parameter, it's coming into play because it decides how we are welding these two disks together.
Yeah. So both the green disk and the blue disk have the same gamma.
Exactly. Yeah.
Thank you.
Yeah. So that's necessary for the result to hold. It's an interesting. One can ask what happens if one tries to do some mismatch, but that's completely open at this point. If one tries to have different gamma values, for example, but that's completely that's out of reach at this point. What happens in that case? Yeah. Are there any more questions?
Yeah, and after the welding, one gets the singularities which are, I mean, like on the left-hand side.
Exactly. Yeah. So there are somehow a number of maybe somewhat surprising things that happen at the same time. So it's somewhat surprising that when one glues these two disks together, one actually gets a new disk with a particular singularity. So that's not obvious at all. It's also not obvious at all that the interface is an SLE. And the third thing, which is quite surprising, is that this SLE, it actually happens to be entirely independent of the LQG disk, which is in the background. Yeah.
So this interface is uniquely determined by, I mean, or is it unique, or is there some freedom?
So it is, if you're given these two disks, then it is uniquely determined modulo the application of conformal map. Yeah, but you can say that it's essentially uniquely determined.
Yeah, so uniquely determined up to Möbius maps.
Exactly. Yeah.
Thank you.
Okay, thanks. Yeah, so that's basically essentially, so the last question is essentially about the uniqueness in this conformal welding. Yeah, so that can be verified in the case of this setting.
And what is rho minus rho plus on the previous slide?
So they are parameters that describe the SLE kappa rho, and they are given by this formula. So the singularity that you have at these 2 points is determining the precise law of the curve that you have on the left-hand side. Yeah.
Okay, thank you.
Yeah, thanks. Okay, so so next I want to present an application of the conformal welding result that I presented on the previous slide. So here we are considering an SLE kappa rho in the unit disk, which connects the points plus minus I. So this SLE kappa rho, it will divide the unit disk into several connected components. And with probability 1, there will be a unique such a connected component which has the point 1 on its boundary. So this connected component is shown in light blue in the figure. Then we consider a conformal psi, which is taking this light blue domain and which sends it to the unit disk, which is fixing the location of 1 and which also sends these green points to the points plus minus I. So with Anjensen, we prove an explicit formula for the moments of the derivative of psi evaluated at 1. So you can see that our formula involves the function f, the function alpha, and also some parameter lambda 0, and these are defined here. So we first let q be 2 over square root kappa plus square root kappa over 2. Then we define the double gamma function by this integral. To be more precise, we use this definition if the real part of z is positive, and otherwise we define the double gamma function by analytic continuation. Then we define the function f as a ratio of double gamma functions. Then we define the function alpha of lambda implicitly by the quadratic equation in the 4th line. And finally, we define lambda 0, as you can see in the last line. So the precise form that our formula is taking is not so important to recall. The main takeaway is simply that we are able to write down an explicit formula, and it's also interesting to observe that our formula is involving this double gamma function. So this is interesting because this double gamma function is probably most well known because it appears in several settings in conformal for several situations in conformal field theory. Okay, so as mentioned before, our proof is based on using these couplings between SLE and LQG. And we're also relying on exact formulas from Liouville conformal field theory and exact formulas for planar Brownian motion. So when proving exact formulas for SLE in general, the most common technique is probably to use Ito calculus and the definition of SLE via what is called Liouville chains. So these more classical methods, they don't seem to be able. It doesn't seem to be possible to derive this formula via these classical methods. And it's quite interesting to see that our proof technique, which is based on this coupling between SLE and LQG, can give us results that are purely about SLE without involving LQG. Okay. So finally, I can remark that mark on the geometric interpretation of this psi prime of 1. So one reason it's an interesting observable to consider in the first place is because psi prime of 1 is giving some way of quantify how close the SLE kappa rho curve is coming to the point 1. And by conformal invariance, we could have considered we could also have obtained a similar formula for 1 replaced by an arbitrary other boundary point. Okay, so as mentioned before, the starting point of our proof is the conformal welding result that I was presenting before. So we're actually also deriving a more general variant of this conformal welding result. So in this conformal welding result, then this blue disk, it's having a third logarithmic singularity on this boundary, which is having some arbitrary magnitude alpha. And we're proving that if we can weld these two disks, we can still weld them together, and we're still getting a new disk decorated by an SLE type curve. But now the disk we get, it will have this alpha log singularity on its boundary, and the law of this purple curve, it will no longer be precisely the law of an SLE kappa rho. So this purple curve, it will have it will be a random curve whose radon-Nikodym derivative with respect to SLE kappa rho is given by the derivative of psi at 1 to some explicit power.
Could you recall what is psi?
Yeah, so psi is the conformal map, which is sending this blue domain to this disk, and which is also fixing the location of plus minus I and 1. So it's just a map from this blue domain and to this blue domain, a conformal map.
And what is capital Q?
Oh, okay, that's actually a good point. So that's it's defined here. Yeah. Okay. And
and alpha is the coefficient in front of the logarithm.
Yeah, exactly. Yeah. So we can insert some. We're inserting some arbitrary logarithmic singularity or with an arbitrary magnitude, and then this has the effect of, first of all, we also get the same singularity on this side, and second of all, it also changes the law of this curve. So it tilts the law of this curve so that according to this term that you can see here.
Thank you.
Okay, so on the next slide, I am sketching how one can use the conformal welding result shown here in order to obtain the formula that I show here. So the idea of the proof is that we look at this conformal welding result, we look at this boundary arc L, and then we compute the law of the length of L in two different ways. So we can compute the law of the length of L in one way by using the left side of the welding identity, and we can compute it in another way by using the right side of the welding identity. So when you compute the law of the length of L from the left side of the welding identity, then our formula will involve this moment. The reason it will involve this moment is because of this particular form that the radon-Nikodym derivative takes in the result, in the conformal welding result described here. So we have these two different formulas for the law of the length of L, and we can set these two formulas equal to each other, and we can solve for this moment. So this and in this way we get some explicit closed formula for the moments of psi prime evaluated at 1. So the next I need to explain is how we can compute the law of the length of L using the left and the right sides of the welding identity. So we will be using primarily two different inputs that I will be presenting on the two next slides. So the first input is a result due to Remy and Zhu. So they are considering LQG disks with two beta singularities and one alpha singularity, and then they are obtaining an explicit law for the length, for the law of the length of this blue curve L. It's not so hard to see that the law of the length of L, it's given by some explicit power, as you can by some explicit power law. What is quite hard is to identify the constant in front of this power law. And this is what Remy and Zhu are doing in their work, and they're proving that this constant is given by the formula that you can see here. And they are relying on tools from Liouville conformal field theory. So the second input that we need is that we consider LQG disks with two marked boundary points, and then we get an explicit formula for the joint law of the left and right boundary lengths. So, for example, in the case when we have two alpha singularities, then this is the joint law for the left and right boundary lengths. If we have these two singularities, then this is the joint law for the left and right boundary lengths. And we're actually only able to compute this joint law in the special case of these two singularities. So this formula on the previous slide, it was relying on these techniques from LCFT. So the proofs on this slide, they're using a completely different technique. So for the results on this slide, then we're using an encoding of a Liouville quantum gravity disk in terms of a correlated planar Brownian motion. So this is known as the mating of trees framework, which was first introduced by Duplantier, Miller, and Sheffield. So these exact formulas that you can see on the slide, they are coming from exact formulas for a correlated planar Brownian motion. By combining this result and this result, we're able to compute the law of the length of L by using the left and right sides of the welding identity. Okay, so that's all I wanted to say about the integrability of the SLE conformal derivative. So I can then go over to the second application unless there are any questions first. Okay, so the second application will be quite short. So this will be the application to random planar maps and the SLE 8/3 loop. So with Anya and Sun, we prove that if we consider two gamma LQG disks, then we can conformally weld these two together, and this gives us the gamma LQG sphere decorated by an SLE loop, such that the kappa value of the SLE loop is given by gamma squared. So this result, it has one interesting corollary, which I have illustrated at the bottom of the slide. So in the left part of the figure, we have a planar map with a sphere topology, and we are and it has been decorated by a self-avoiding loop. And by combining our result with results of Ogun and Miller, we can show that that the scaling limit of this object is given by an LQG sphere decorated by an independent SLE loop. In the special case when kappa is equal to gamma squared is equal to 8/3. So this SLE loop with kappa equals square root of 8/3, it is believed to describe the scaling limit of self-avoiding loops on regular lattices. And by using this result, we obtain the counterpart of this conjecture in the setting of planar maps. Okay, so next I want to explain an application to the partition function of LQG surfaces with marked points. Okay, so first, so we start by considering a planar map with a loop of N model. So we consider a random planar map M, which has been sampled such that the probability that the planar map is equal to some fixed map little m. It is proportional to the loop O of N partition function on little m. So earlier in the talk, I was mentioning very briefly that if we sample a planar map in this way, then we are believed to get a Liouville quantum gravity disk in the scaling limit. What is actually also believed to hold is that if we consider this planar map and we sample the loop of N model on top of that planar map, then the loops, they are believed to converge to the conformal loop ensemble. So the parameter kappa of the CLE and the parameter gamma of the LQG, they are given by these explicit formulas where N is the parameter of the loop of N model. To be precise, this conjecture is only believed to hold in what we call the dilute case. So the loop of N model can be in several different regimes. And just to be concrete, we're considering only the dilute case in this talk. In our paper, we're also considering the dense case, which is a little bit different and is actually also quite interesting. So now we consider a generalization of the model on the previous slide.
Yeah, well, can you explain what is the ON model? I mean, ON model on something on
yeah.
N?
Yeah, so maybe I should have explained this as well. So it just means that if we have a configuration of loops on the planar map, so then we can. So if we're given some lattice, for example, a planar map, then we can give a weight to each possible loop configuration on the planar map. And if we have for some given loop configuration, then the weight is just given by taking some parameters. So the thing is, the loop of n model, in addition to the parameter n, it also has two additional parameters, which are called sometimes called g and h. And then one can, for example, take and then the weight of a configuration is given by g to the number of for example, triangles that are crossed by a loop, and then h to the number of triangles that are not crossed by the loop. And then one also takes n to the power the number of loops that one has. Yeah, so maybe I should have included a formula for that on the slide.
And why is it called ON? Where is the Euclidean? Where is the orthogonal group here?
I am actually not entirely sure about the origins of the name. Yeah, maybe there are some other people in the audience who knows. I am actually not entirely sure myself.
It's related to the n-component spin systems.
Yeah.
Except that these are the loop ON, which are kind of classic, kind of like the classical spins with some approximations. So yes, so the ON is the symmetry of. I mean, there should be some kind of ON symmetry behind that.
Okay. Yeah. Thanks. Yeah. Okay. So. So that's the definition of loop ON, and here we are considering a generalized version of this model. We consider the setting where the planar map has additional mark points. So for some natural number m, we consider planar maps that have m mark points. And then for any subset of points, then we let n sub b be the number of loops surrounding precisely the points in B. So for example, we have n sub 1 equals 1, since there's one loop around this point. We have n2 equals 2, and we have n12 equal to 0, because there are 0 loops around both points. Then for each subset of points, we also have some real parameters, sigma sub b, and we have also a parameter lambda, which is greater than or equal to 0. So now we are sampling a planar map at random, such that for a fixed planar map little m, then the probability that our planar map is equal to little m is again proportional to the loop of n partition function. But now we are also multiplying by the expectation of this term, depending on the nesting statistics. Where when we take the expectation here, we're averaging over the random loops on this fixed map little m. And then we're also here multiplying by e to the power minus lambda times the area of the planar map, where the area is just the total number of vertices. Because we imagine that when we sample a planar map, then the number of vertices on the boundary is fixed, whereas the number of vertices in the interior is a random variable. Okay, so as we're arguing in our work, what should be the scaling limit of the model on the previous slide? So in the setting of 0 mark points, we should get some LQG disk with a CLE on top of it, and we're arguing that in the setting of additional mark points, we should get some variant of these objects. We're not giving a rigorous proof, but we are giving some heuristics. So I want to explain what these objects are, but first I want to just give some heuristics in the setting of planar maps. Just to be concrete, we assume that lambda is equal to 0, and we assume that all the sigmas are positive. So if all the sigmas are positive, then we're favoring configurations where there are lots of loops around the mark points. For example, for this point x2, we're favoring configurations where there are lots of loops around x2. So this means that we will favor planar maps, which have a huge density of vertices around x2. We will favor such configurations because if there are a huge density of vertices around x2, then there will be a lot of room for adding a lot of loops around x2. So this is explaining why doing such a reweighting as described on the previous slide, it should reweight the law of the field describing the limiting surface. And we're arguing in our work that what should happen is that the law of the field H should be reweighted according to this term when we introducing this expectation should reweight the field according to this product, where the parameter alpha j is related to the sigma j by this formula. I will be coming back to this formula in a minute. So it's not so hard to argue that if we have the field H and we reweight according to this, the law according to this term, then this corresponds to adding logarithmic singularities to the field. And it turns out that the resulting field that we get when applying this reweighting, it's actually identical to a field which is arising in Liouville CFT, and which was introduced in the work of Huang, Rhodes, and Vargas in the math literature. And similarly, we also get a reweighting of the CLE. Okay, so on the previous slide, I was introducing this object, which is given by an LQG disk with marked points where there are logarithmic singularities, and then which is also decorated by this collection of loops, which are given by some reweighted CLE. So there's one interesting result that one can prove about this object. This CLE, it will divide the LQG disk into smaller LQG surfaces. For example, we have one LQG surface, which is the one inside this loop. We have another LQG surface, which is the one inside this loop, and so on. And then it's possible to argue that these different LQG surfaces, they are actually independent of each other. And additionally, the law of these LQG surfaces is actually identical to the law of the surface we started with, conditioned on the boundary length of the surface and on the number of marked points falling into the surface. So for example, this disk we started with, that's what we can call an LQG disk with 4 marked points. The surface, which is inside this loop, that's what we call an LQG disk with 2 marked points and with the given boundary length, depending on the boundary length of the red loop. This is an LQG disk with 0 marked points and so on. So this result is not surprising at all, because in setting of planar maps, then it's easy to see that the exact same property is holding. But the proof of this property is done purely in the continuum using very different ideas. So next, I want to define the partition function of the surface on the previous slide. So the surface that you see here, it can be associated with a number of parameters. So we have the parameters sigma and lambda, which are the one we are reweighting with in this construction that you see here. Then we also have the kappa value of the CLE, and we also have some positive parameter L, which is giving the boundary length of the disk. So remember that when we obtained this disk from the setting with no marked points, then we were reweighting by these 2 terms in blue. So therefore, it's natural when defining the partition function of this surface. It's one can start with a partition function in the setting of no marked points, and then one multiplies together the 2 terms that one reweights by. Then one takes an expectation and one integrates over all possible locations of the points. So this should actually be d to the power m. Okay, so it's not straightforward how to make rigorous sense of this definition of the partition function, because it's not obvious how to make rigorous sense of these terms in blue. The first thing, in order to try to make rigorous sense of it, the first thing that one can observe is that these 2 terms in blue, they are independent, so therefore the expectation is factorizing. Making sense of the expectation of the first blue term is actually not so hard because the field age is Gaussian, so it can be computed. Making sense of the expectation of the second blue term is much harder, and one reason it's hard is because if B consists of a single point, then n sub B is actually infinite, because if we consider some fixed point and we look at the number of loops around this point, then the number of loops will almost surely be infinite. In this figure, you can see only the outermost CLE loops, but the CLE loops are actually nested. So it's not obvious how to make sense of this term, but we are showing that it can be done by applying some renormalization. And when we are doing this, then we are in particular using and deriving some strong spatial independence results for CLE, and also applying an explicit law for the conformal radius of a CLE, which was derived by Schramm, Sheffield, and Wilson. And this explicit formula, due to Schramm, Sheffield, and Wilson, is also can also be used to explain this relationship between the sigma and the alpha. Okay, so we have defined this partition function z. So one reason that this partition function z is interesting is because it is believed to describe the scaling limit of the partition function of the model on the planar map. But it's also of interest because it has a close relationship to Liouville CFT. So it's possible to argue that this formula in the formula holds. So this is a formula which is giving an explicit relationship between three very interesting functions. So the first function is this partition function. The second function is this function phi that describes properties of CLE. And the third function is this constant c. So this constant c is a constant which is closely related to what is called the Liouville CFT correlation function. So this is the observable of which has primary interest in LCFT. So to be more precise, one can get the correlation function by considering this constant c and then integrating over all possible values of L. Okay, so it's interesting to have this relationship because one could hope that if one knows two of these functions, then one could try to also compute the third one. So this function phi, it is interesting because it's a natural observable to consider for CLE, but it's also of interest because it is related to something known as imaginary LCFT. So when working with LCFT or Liouville CFT, one is normally the parameter gamma of the LQG is normally assumed to be real, but a number of objects actually also can also be defined when gamma is imaginary or complex. And the case of imaginary gamma is particularly interesting because it is related to the problem of constructing a CFT for CLE. Okay, so going back to these partition functions, so in our work, we're deriving a recursive formula for these partition functions. So first of all, when the number of marked points is equal to 0 or 1, then we have an explicit closed formula. And when the number of points is strictly greater than 1, then we have a recursive formula for the partition function. Okay, I'm not sure how much time do I have left?
5 minutes, yeah.
Okay, then I think I'll finish, yeah. Okay, so when we derive this recursive formula for z, then we are using the result described on this slide. So on this slide, you see that we started with a disk with 4 marked points, and then using this CLE on top of the disk, we are breaking the disk into smaller disks, which have strictly fewer than 4 points. And by using that result, one can argue that the 4-point partition function can be expressed in terms of lower order partition functions. So we have some recursive formula for z. So this formula is quite complicated. One reason it's quite complicated is because it also involves the joint law of all the loop lengths of the CLE loops. So we need to know the joint law of all the loops, of the length of all the loops that you can see here. It is possible to derive this law by using a continuum counterpart, or what is known as a peeling process in the setting of planar maps, which I will not be going into here. But the formula is quite involved. And in our work, we're not making any attempts to simplify this recursive formula and to derive some explicit closed formula. But what we do is to use this recursive formula to address the admissibility question. So we are partly answering the questions of which parameters that give us a finite partition function. So if the number of points is 0 or 1, then the partition function is always finite. So that's simply a consequence of the explicit formula that we have in that case. When m is greater than or equal to 2 and lambda is equal to 0, then the partition function is always infinite. So remember that lambda is this parameter which is given an exponential penalization according to area. So then if lambda is strictly positive, and if also sigma sub b is strictly smaller than sigma sub I, if the number of points in B is strictly greater than 1, then on the other hand, the partition function is always finite. But finally, if we pick some arbitrary subset B of points which consist of strictly more than 1 point, then if we let sigma sub b be sufficiently large as compared to the other sigmas, then we don't have admissibility anymore. Okay, thanks.
Thank you very much, Nina, for this very nice talk. Questions or comments from the audience? So I think I have one. About this last result you were mentioning, can you go back to slide 27?
Okay, yeah.
So you said that, there is this relation between the, this last formula Z on the left, and then on the right hand side you have phi and C. And yeah. So the phi, these are the correlation, no, sorry, the C, these are the correlation functions of the Liouville CFT, which I guess they are known, right? Or, you compute the Z without knowing those guys, as I understand.
Yeah, yeah, exactly. So, so currently we don't have any closed formula for any of these actually. Unless maybe if the number of points is sufficiently small, but for in general case, we don't have currently there is no closed formula for any of these three.
So this product of exponentials of the Gaussian free field, the average of this guy, that there is no closed formula for that.
You mean so what corresponds to
right.
to this term?
Yeah.
So I guess in the case of only the Gaussian free field, one can do it, but it's more complicated when one also has this cosmological constant, or this lambda,
right,
this lambda present.
Mm-hmm.
Yeah.
I see. Okay. And so when you mentioned, these identities with the quote unquote sign, that there is some renormalization involved there.
Yeah. Yeah.
Fine.
Yeah.
Okay. So there is one notion of renormalization for the first product, and then you said there is a.
Yeah. Exactly. Yeah. Yeah. So there are, in the case of the GFF, one is just using, there are several ways to proceed. One can use what is called a circle average approximation, which one just replaces age by the average of age on some small circle around the point, and then one takes a limit. Yeah. And in the case of the CLE, one can use, it's a similar idea where one first just considers loops that are above a certain size. And then one sends the cutoff to 0 and renormalizes.
Okay.
Yeah.
Thank you. Yeah. Other questions or comments?
Yes. So I'd like to try to understand the second application. So the self-avoiding loop on random planar map.
Okay. Yeah.
Could you explain the statement, especially what is the object in the left-hand side?
Okay, so the object in the left-hand side, I guess it's
actually, that one.
Yeah.
That one.
So it's actually it's actually a little bit of a maybe more complicated object than what I was giving the impression of in the talk. So it's so what one would do is just so to each such, consider a planar map with this spherical topology and decorated by a loop. And to each such object, one is assigning a certain weight.
Yeah.
And the weight depends on the number of vertices of the planar map, and it also depends on the length of the loop. So in particular, one is giving the exact same weight if one has two different objects where the loop length is the same and the number of vertices of the map is the same, then they will get the same weight. And
so,
yeah,
who invented this weight, or who invented this stochastic geometric system? Is it something standard, or did you cook this up to?
no, this is a quite standard thing.
Okay.
Yeah. So it's so if one considers only the planar map, then this weight then one considers when we're typically there is some constant. We consider some constant to the power of the number of vertices. That's the weight one is typically using. And if one tunes this constant, one can tune this constant in a very particular way, such that which is somehow the critical way of tuning the constant, which is giving the total. If one looks at the law of the total number of vertices under such a reweighting, then it has a power law behavior. So there is somehow there's a very natural way of giving a weight to such an object.
Okay, thank you.
Yeah. And what is also quite interesting is that one is actually not working with probability measures in this result. One actually has to work with, it's more natural to work with infinite measures. So somehow both this gamma LQG sphere and this SLE loop, they're actually not probabilistic objects in the sense that they have total mass. It's not described by measures having total mass 1, but they're described by infinite measures. So that's somehow the natural, that's somehow the setting where the result takes the nicest form. One can also formulate versions with where one there's various ways of restricting the measures so that one gets finite measures. But I mean, one can still formulate it, but it's not as the results are not as nice stated in that way.
Other questions, comments?
So I also wanted to ask some questions about self-forwarding loops, because a major open problem is to prove that the self-forwarding walk converges to SLE 8/3
Yeah.
regular graphs. So can you, for instance, consider the self-forwarding walk on a random planar graph?
Yeah, so that has actually been done. So that's actually in this work of Gunn and Miller. They wrote a series of papers on this, and they are actually able to do this in the setting of planar maps.
I see.
Yeah, so they are doing it in the setting of infinite volume planar maps, because then they're actually able to say that the limiting curve is an SLE 8/3. And then we are relying on some of their techniques, and then by and so we are relying on their result to say that also in this setting of finite volume surfaces and in this setting of the loop, one also gets SLE 8/3. But they were the first who obtained convergence to SLE 8/3 in the setting of planar maps.
Thanks. And could you also consider other, I suppose, some random graph, but with different measures than the random planar graph?
So that's, I mean, it's actually still believed to be true. So it's somehow believed to be true that for any kind of reasonable planar map model with some self-avoiding loop or self-avoiding path, then it should give SLE 8/3. The techniques are actually quite specific to very particular planar map models. So namely, one needs the planar map to somehow be reweighted by the partition function of the model. So the planar. So if you look at the marginal law of the planar map considered in this result, then it is reweighted by one needs to also make a sum over all self-avoiding loops on the planar map. So it's not somehow not entirely uniform in that sense. So it's yeah, so we definitely need a very specific law on the planar map in order to be able to get these results.
Again, thanks a lot.
Yeah, thanks.
Other comments? Okay, doesn't seem to be the case. So thanks a lot, Nina, again, for the very nice presentation.
Thanks.
Thank you.
You can stop